Okay, guys, I think we can probably get started. Thank you guys all for coming. My name is Sara Swett. I am an extension specialist with Oregon Sea Grant, based in Corvallis, Oregon. And we are super excited to have this presentation for you guys today. We're going to learn a lot about PacWave and the monitoring program there. I just put this picture up to, give you guys an example of what a wave energy device looks like. This one is in Portugal. And to give you guys a little bit of background about Oregon Sea Grant, we are a cooperative agreement between the National Oceanic and Atmospheric Administration, NOAA, and Oregon State University. Our purpose is to serve the Oregon coast by addressing important topics and issues with neutral science-based information. We are a non-advocacy organization, which means that we do not promote or oppose the development of wave energy off of the Oregon coast. The intent of this webinar is to be informative and educational and to help answer some questions about what type of research is happening out at PacWave. We work in these 4 focus areas all along the Oregon coast and throughout our program. And to address these different focus areas, we work through extension, which is what I do, education, and through research. So today we are going to get into our presentation at 10:10, and that presentation will go for about 40 minutes. And then at 10:50, we'll head into our question and answer and discussion. Before the presentation, I've got a little pre-webinar poll for you guys. And then after our discussion and presentation, we'll do a post-webinar poll. So our learning goal today is to understand how researchers are studying the seafloor environment at PacWave and using baseline data to assess potential ecological effects of wave energy devices and infrastructure. And thank you again to Dr. Sarah Henkel for joining us to give this presentation today. Sarah is a benthic ecologist at the Hatfield Marine Science Center in Newport, Oregon, which is part of Oregon State University. And she's also been the acting director of the Pacific Marine Energy Center at Oregon State University, which they've got their logo right here on their slide. They are really one of the leading research centers in our region that looks at offshore renewable energy and just marine energy development. She's the environmental studies lead for PacWave and serves on the leadership team for the Pacific Offshore Wind Consortium. Her research broadly addresses potential effects of human activities like marine renewable energy, installations, marine reserve designs, coastal development, invasive species, and environmental change on seafloor habitats and species.
Thank you, Sarah.
Yeah,
and I'm happy to announce that Bryson is back. And at 1 p.m. today, after this webinar, I'm going to hand the baton back to him, and I will just be an associate director and no longer have to act like the director of the Pacific Marine Energy Center. So for anyone who knows Bryson, he's back in the States. So I'm a benthic ecologist. And so I'm going to focus on the Benthic and EMF investigations that I've been undertaking. Most of the content of this webinar will focus on PacWave, but I'm going to start broader and give a little bit of the history of both wave and offshore wind in this region to set the stage and really emphasize how long some of us have been working on these questions and what's been accomplished so far. So first, why would we go offshore? So this is a figure that we have been showing for probably a decade or more, but it holds true, and that is that most of the US population is concentrated on the coasts. And so we want to generate energy where most of the people are located. As opposed to, certainly there are opportunities for wind and solar in Central or Eastern Oregon. And, I'm a fan of all renewables, but you can see that generating electricity offshore is going to be much closer to most population centers in the United States. The map on the right shows the US wind resource, but where there's wind, there's waves. And so you could interpret this also as a US wave resource map. When we talk about ocean renewables, there are many types of ocean renewables, and we categorize them into two subcategories. So tidal energy, current energy, OTEC, which stands for ocean thermal energy conversion, and wave. We consider those MHK, marine hydrokinetics, because the energy is generated from the movement of water, and in this case, seawater. So kinetics being movement, hydro being the water. And that is different from offshore wind, where it's the wind that is generating the electricity. So considered to be different sources of energy, but as a marine ecologist, I'm not concerned about if the energy is coming from wind or waves. Most of the concerns that I've been involved in addressing, it doesn't matter if it's wind or wave. When we focus on hydrokinetics, this is again tidal, wave, OTEC, or current. The Pacific Marine Energy Center has mostly focused on tidal and wave because we are a consortium of Oregon State University, which is in Oregon, which has a very straight coastline without barrier islands. And so wave is a really attractive resource in Oregon because we have them and they're very predictable. University of Washington historically has focused on tidal energy, located on Puget Sound, where there's many places where you can get strong tidal exchanges. We added University of Alaska Fairbanks, and they are more focused on, I would say, river than offshore energy generation at this point, so you could consider them current. The reason that we like hydrokinetic renewables is because they're persistent. The water never stops moving. The winds do stop blowing. Solar turns off at night, but if you're a coastal resident, there are always waves, there are always tides. The magnitude of them might vary, but again, they're quite predictable. You can download a tide table for next decade. And in terms of waves, again, because Oregon has a straight coastline and no barrier islands, when we get data from the offshore buoys, our models of what those waves will look like when they get to the nearshore are very reliable. So, focusing on wave. So the wave energy efforts in the Pacific, I'm going to take us back 2 decades to the establishment of the wave energy test site off Marine Corps Base in Hawaii. And the power buoy, a 40 kilowatt power buoy, was deployed there in 2004. Some local residents may remember that in 2007, a wave energy buoy was deployed off Newport, Oregon. It did unfortunately sink to the bottom. I think that the day before it was set to be recovered, but the buoy was insured and the company did recover it. Weeks later, days later, really, we held the first ecological effects of wave energy development workshop at Hatfield. The following year in 2008, NIMRIC was what we used to be called the Northwest National Marine Renewable Energy Center with Oregon State University and the University of Washington was established. And then I came in 2009. We also had a buoy test off Newport in 2008. In 2011, Aquamarine, which has the Oyster device, leased offices in Newport, Oregon, but never did do a deployment. In 2012, we tested the Columbia Power Technologies device, which is now known as Sea Power, at our PacWave North site. In 2014, the wave energy test site in Hawaii added 2 more berths. And since then, a number of devices have been deployed multiple times. Within this big overview timeline, we did kick off the PacWave process. So our feasibility study began in 2011 And we had about 2 years of site selection process. So we first held meetings in Warrenton, Newport, Reedsport, and Coos Bay to assess community interest in having the wave energy test site in those locations. Community site selection committees were formed in each of those 4 communities and included a number of different groups. In September of 2012, based on those community meetings, the focus narrowed to Newport and Reedsport. Those were the 2 communities that expressed the most interest and met some of the physical requirements for ocean conditions and infrastructure. Proposals were submitted in December of 2012, and Newport was selected in 2013 as the location in general. And then many people, but mostly through working through FINE, the fishermen involved in Natural Energy Committee, we determined which site off Newport would be the PacWave site. Here is an artist conception of what PacWave was going to look like. Again, this is a figure we've shown many times over the years, and every single time we have to say, like, it's not this close to shore. The artist, I think, wanted to make a very concise drawing, but the site that we've picked is about 7 miles offshore. If you're familiar with the local area, the site is kind of off where the airport is, just south of Newport. So then we picked the site in 2013 and had meetings for 6 years. 6 years of meetings about exactly what was going to happen there, what would be allowed, what environmental studies. And then we submitted our final license application in 2019. The BOEM lease and the first FERC license were issued in 2021, and we started construction. BOEM is the Bureau of Ocean Energy Management, and they are the organization from whom we need to get a lease to use that piece of the seafloor. And then FERC is the Federal Energy Regulatory Commission, and they are the ones that we have to get a license to generate electricity. So when we started construction, we started both directional drilling under the beach to lay conduit for which the cables would go through in the future. And then we also started building our universal connection and monitoring facility, which is where clients who will be wave energy developers who want to test their devices at the site can, for example, in this big garage door, they could back in a big trailer and have some of their things on there, whatever they might want for monitoring the power. And then we also have a building like with a conference room for meetings and whatnot. So we directionally drilled conduit from the Driftwood State Wayside to a mile offshore to lay the cables through. And then we also drilled conduit from Driftwood State Wayside south along 101, and then from the Universal Connection and Monitoring Facility north along 101. And this is, I think, incredible. So we hired a organization out of Louisiana who is familiar with doing this kind of work. The oil and gas industry does it all the time. But a marine ecologist, I was just so impressed that they could start at Driftwood and drill south, and start at the UCMF and drill north. And these conduits are 50 feet underground, and they met up exactly when drilling from both ends. Just a really incredible operation. This is a picture of the Driftwood State Wayside with the 2 drill rigs drilling the conduits offshore. Part of our agreement with the parks was that we would improve the site after we were done. So if you go to Driftwood State Wayside now, it's a beautiful parking lot with a new viewing platform and sidewalks, and it looks really clean and lovely. And you can also see the vault lid, which we could open if necessary to service the cables. So that drilling process took about a year, 2021 to 2022. We thought we would finish construction in 23, but of course, projects never go the way you think they're going to go. So in 2024 is when we actually laid the cables. So they pull them through the conduit and then lay them on the seafloor all the way out to the site, which we have a really diagonal cable route to avoid some rocky reef that is off of Newport further north. So each of these cables is about 12 miles instead of 7 miles if we'd gone straight offshore. So we've got about 50 miles of cable. So the way the process worked is they were laid on the seafloor by one ship, which is not pictured here. And then a second ship came that has an ROV that I call, this is my own thing, the underwater ditch witch. So if you've ever rented a ditch witch to make some sort of trench in your yard, it's like an ROV, a seafloor version of that. And so it makes a trench and pushes the cable into the trench. Because in my mind, the concerns about wind and wave are similar in a lot of ways. In terms of Pacific wind energy efforts, some of you may remember that WindFloat Pacific was proposed in 2013 to be a pilot project of 5 turbines off Oregon to demonstrate the potential of what at that time they called deep water floating wind. About 450 to 525 meters was the site that they had requested from BOEM. And then in 2016, there was a Morro Bay project proposed that would have consisted of 100 floating systems in 700 meters deep water. And our recent Oregon wind energy activities that were happening while we were doing the PacWave construction, where the call areas were released in 2022. This map shows 2 of them. Some of you may remember that there were actually originally 3 call areas released. There was a lot of pushback for the site off Port Orford. And so BOEM took that one off the map early in the process. After some public feedback, the call areas were reduced to the draft wind energy areas that were considerably reduced. And then we were supposed to have the auction in October of 2024 for the slightly smaller proposed lease areas, but it was postponed due to lack of interest and given the federal landscape, not likely anytime in the future. So what are the potential environmental effects of wave or offshore wind that as an ecologist, I'm interested in studying? So this figure, again, is one that I started using when I started this job in 2009, where we're concerned about things like potentially lighting from surface elements, maybe some chemical release from anti-fouling paint, or if there were some sort of hydraulic fluid in there. But then really the big thing is that there are structures we're putting in the ocean. So those structures, the anchors could have scour around the anchors. They could be colonized by fouling organisms, because if you put something hard in the ocean, it will get colonized by fouling organisms. Maybe attract species that are normally associated with rock. And then also potentially the reduction of wave energy by the devices themselves could affect sand transport and sedimentation. Concerns about noise from the devices and potentially from electromagnetic fields emanating from the cables or the devices themselves. And then here, Farr et al. Published this paper in 2021, which was a synthesis of 89 existing articles about potential environmental effects of deep water floating offshore wind. And you can see that the stressors, the parts of the device that might interact with the environment, and the habitat and the environmental concerns are largely the same. So pretty consistent evaluation of potential environmental effects over the decades. And here, after the synthesis of 89 articles, most of the potential magnitude of environmental effect is considered minimal to moderate. So as a benthic ecologist, for the remainder of this presentation, I'm mostly going to focus on seafloor habitat alterations and potential EMF effects on benthic species. And I'm going to check the chat for any questions. Okay, just Karina's defining EMF for me. Thanks, Karina. So starting with the wind float site, as that was sometime before the PacWave, well, I guess it was consistent with the PacWave project. So when the wind float Pacific site was proposed in 2013, BOEM, the Bureau of Ocean Energy Management, funded surveys. They funded the US Geological Survey to map the requested aliquots using multi-beam and backscatter. And then jointly, my team and USGS conducted 17 dives, these little red squiggles, with a benthic sled with video on it to quantify mega invertebrates and fishes. And as part of that process, we identified cobble field pockmarks as a special habitat. And then from 2014 to 2016, we took bottom grab samples at the site. So here would be the cable route of the proposed site and the site itself. And then we sampled all up and down Oregon, well, mostly north of there at similar depths. And this complemented some BOEM-sponsored sampling of the shelf that we had conducted 2010 through 2012. And so BOEM's really been supportive of the seafloor investigations for both WAVE, which is what motivated these shelf investigations, and offshore wind, which is what motivated these slope surveys. Of course, now I've added, these are the two wind energy areas that were set to be leased in the fall. And of course, as soon as you sample one place, now there's a proposal to sample for the project to be deeper. That was exactly what happened. We sampled all these, and then wind float proposed there. We sampled all these, and now the new areas are further offshore. We have not yet box cored those areas because there has not yet been a lease request by a developer specifically for those sites. But this Express project, which is a collaboration between the Bureau of Ocean Energy Management, NOAA, USGS, the Monterey Bay Aquarium Research Institute, and University of Southern California Sea Grant, they have been doing mapping surveys, dives, and sampling all through Oregon and California. And so those projects have surveyed the potential wind sites. All right. So back to WAVE and back to our local sites. So in terms of environmental surveys, we've been conducting at the PacWave sites. So here is the official site that was selected for PacWave South. And we also had a site that we had permitted that was not grid connected, that has no cables, that we call PacWave North. I've been conducting benthic invertebrate and sediment grabs at PacWave North since 2010 and PacWave South since 2013, with some breaks in there as we did site characterization studies. Started to recontinue that time series after we submitted our lease request. Then we had COVID, so I didn't get out there in 2020, but since then have been doing benthic grabs at the PacWave South site. We did survey a lot of flatfish at the PacWave North site before we started any sort of activities there, but I felt like I probably killed far more fish doing the surveys than we ever would for a project. So taking a hiatus on that until we have something to survey. We've been conducting seafloor videos. We did in 2012 and 2024 at PacWave North, and we've been continuing that time series at PacWave South. As part of site characterization, we did Dungeness crab pot deployments at all the places where there's little circles. So south of the PacWave South project, in PacWave South, and north of there. And something that was really interesting is that for the 2 years that I did Dungeness crab surveys, the sampling location that was in the PacWave project always had the lowest catch of crabs. So complete coincidence, but really interesting, and we can follow up on that when we have something actually happening at the PacWave South site. In all of these benthic invertebrate surveys, trawl surveys, video surveys, we often have marine mammal or bird people on board to make ship-based observations. So these lines are representing how we take the boat amongst stations. And so all of those lines are available for surveying mammals and birds. These little pyramids indicate places where we've placed hydrophones to listen to how noisy the ocean is right now, to characterize what is the soundscape and how might that change as we deploy devices. And then we have done some electromagnetic field mapping of the PacWave site, and we're also conducting lab studies. And so I will take us a little bit deeper into these two issues. So in terms of electromagnetic fields and fish, so a buried subsea cable conducts electricity. There is no electrical leakage from these cables. We had to go, Dan Helene, our PacWave director, had to go to Norway in the factory, and they demonstrated to him that there was no leakage from the cables before we even accepted the cables being put on the ship. They were certified that there's no leakage from them. The cable is completely electrically shielded, so there's no electric field emitted. However, we can't shield the magnetic field. So there is a magnetic field that is emitted radially into the environment. And the electromagnetic field can interact with the local geomagnetic field. And also, as ions move through the seawater, there can be an induced electric field. So a pretty small field. Part of the way that we mitigate this is by burying the cable so that that emitted magnetic field isn't very much in the water. It's mostly in the sediment. But of course, as we have the cables that connect from the seafloor to the devices, those won't be buried. What do organisms think of this? Well, most fish can detect magnetic fields. I think people usually think about elasmobranchs for electric fields and maybe salmon. But pretty much every group of fishes that have been looked at, it's been determined that they can detect magnetic fields. So these clades highlighted in blue represent orders in which behavioral evidence for magnetoreception has been obtained. And the orange ones are where studies haven't been conducted. So maybe even those fish can detect magnetic fields. So pretty common way of sensing the environment for marine organisms. And of course, cables in the ocean are not new. We're thinking about them more recently because of offshore renewables. But of course, every single oil platform that's ever been deployed out there has a cable to it because they're not turning on those lights from the oil that they're extracting at that site. So we have a lot of cables in the ocean already associated with marine energy. But we're gonna still investigate it. And so, like I said, we've conducted EMF mapping at PacWave. And we're also looking at animal responses to EMF in the lab. As we deploy devices at PacWave, we'll use models to estimate the anticipated EMF output and determine if EMF from the WEC is likely to exceed ambient levels at a distance of 20 meters. So that's our regulatory threshold. We have to accept that there is going to be some field quite near to the devices, but we are looking to ensure it doesn't exceed ambient at 20 meters from the WEC. Within 45 days of deploying the wave energy converter, we'll conduct a field survey to measure the EMF while the wave energy converter is in an energized state, to provide field data to validate the models. And in our license required monitoring plans. We have an off-ramp that if field monitoring from the first 8 wave energy converter tests validates the models, then we only are going to do the field monitoring if the energy generation really steps up to a level we haven't seen before. So if the next WEC is 30% or greater capacity, then we'll go out and do the field monitoring again to make sure that our models are still accurate. In the lab, we've done a number of really fun studies. So we have a big tank in the lab with a cable running underneath. So far we've tested, we've tested 10 each of Dungeness and red rock crab if the cable in going down the center of the tank, and then we've been testing moving the cable around, but here are the data from the 10 with the cable down the center of the tank. And so we've got a tank with the cable going down the center. In this first column, it's off. If organisms were attracted to the cable, we would expect to see them more in the middle of the tank. If they were trying to avoid the cable, we would expect to see them at the northern and southern poles of the tank, if you will. So what's interesting is this was really consistent across all our studies. This is a heat map of where all of the crabs, so layering on basically a map of where each crab was, and then the 10 crabs, all of the Dungeness crabs really mostly hung out in the northwest corner of the tank without the cable on. And interestingly, the red rock crabs kind of hung out in the south and west corner of the tank. So I don't know why Dungeness like the northwest and red rocks like the southwest, but there they are. And so when we turn the cable on, if we had alternating current going through, you can see that the Dungeness moved and hung out more in the south, but they're not particularly really avoiding the cable. They're not clustered down here at the pole. They're not particularly attracted to the cable. They're not clustered right on the cable, but it did stimulate them to move in the tank. And of course, they would have had to cross the cable since they preferred the northwest and then move to the south. Interestingly, the red rock also switched their preferred half of the tank, but maybe you could think they were clustering because some of them are here, but some of them are also here, not terribly avoiding. And then if we have DC, direct current running through the cable, again, the Dungeness are more in the south, but not necessarily showing a strong either attraction or avoidance. They're kind of all around. And the red rock, again, switching a little bit of preference to the north. Are they sort of clustering along this hemisphere? Statistically, no. So under both AC and DC, the Dungeness shifted distribution in the tank, not attracted to or avoiding the cable. They did, when we look at their rate of movement around the tank, they slightly moved slower when we had the alternating current on, and there was no effect on their velocity of the DC current. Under both AC and DC, the red rock also shifted their distribution on the tank, but statistically no attraction or avoidance of the cable. And they slowed down both under AC and DC conditions. So sampling their environment a little bit more before moving around. In the field, we haven't conducted these studies, but researchers at UC Santa Barbara who have access to those cables going out to the oil platforms that I showed you in the earlier figure, they had a really great study. So here's the cable out to one of the platforms. Here they've mapped the electromagnetic field along the cables. And they had these crab pots that had food in both sides, and then this chamber that they would drop the crabs in, and some of them were located along the cable and some of them were just away from the cable as reference conditions. And basically they did not care if there was a cable there or not to get the bait in one side or the other of the modified crab trap. So 49.2% crossed the cable to enter a baited trap, which means 50.8% did not cross the cable to get to the bait on the other side of the trap. So while maybe they're investigating their environment, they certainly are very food motivated and have no problem crossing a cable to get to some food. When I say the crabs slowed down, so the other thing we can do is we have a camera on the crabs all the time. That's how we can get their position. And we also can measure their velocity. So they're just roaming around the tank. And when we had the cable on, they were roaming slightly slower in some cases. So those were all tank tests. And so not necessarily, they're not, we didn't provide them any bait to go after. That was a follow-up experiment I wanted to do based on this experiment from Santa Barbara. But this is just basically their rate of wandering around with the cable on or off. We just did a few other species. So we did, actually we were up to 4 of the big skate and 3 long nose skate, the same kind of thing. For either skate, their spatial use did not change with EMF exposure. You can see that in both sets of heat maps, the skates are basically just going around the tank all the time. The big skates are pretty much constantly moving, so there's no hot spots on those maps. The long nose skate are a much more sedentary species, so each of those hot spots is basically like a skate in one of its trials. We tested each of the skates 5 times since we had a lower sample size. So if you see 15 hotspots, that's probably 15 trials where a skate was just sitting there. Under AC, the big skates, they increased their swimming around the tank by 5.5%, and under DC, they decreased it by 7.4%. So small changes in velocity as maybe they're sampling their environment more or slightly excited. The long nose skates under AC decreased their velocity by just under 10%, but under DC, they really slowed down. So across the 4 species I've described to you so far, the biggest response we've seen is long nose skate under DC, where they really slowed down. We also tested, these data are from 3 fish. I think we have actually tested 6 fish in a much larger tank in the Oregon Coast Aquarium to try to reduce that just roaming around the perimeter that we see with a lot of animals in captivity. And dogfish appeared to show a preference for the east side of the tank, regardless of which cable was energized. So here you can see most of the animals are on the east side where the west cable was on, but then if you turn the east cable on, it's not like they went to the west side. So they just like the east side of the tank. The preference was slightly less east with the DC cable on, but you can see here still a little bit of east preference, and here they're kind of all over. So not much of a response with dogfish, but that is consistent with what some other authors on the East Coast have seen with other dogfish species. They really don't seem to care about EMF. All right, a couple minutes left to really focus on the benthos, on the habitat changes. So we can see there are many ways, and what this figure is showing is, it's looks like an engineering figure, but it's not. It's the different types of activities and how they're connected with either changes to the habitat or changes to animals. And the numbers on the lines are the numbers of studies that have looked at that linkage. And so when we think about the structures changing the hydrodynamics and maybe the granularity or the habitat, here, this is a screenshot of a video survey that we did of an anchor that was deployed. And around the anchor, you start to get scour and some accumulation of shell hash around an anchor. So that would be an example of a abiotic change that might have consequences for organisms. So how do we survey the benthos? A lot of different ways. So we can do sonar mapping. We have video sleds like I described we did at the wind float site. I mentioned video surveys that we've done at the PacWave site. We've done that either with remotely operated vehicles, both of these, or a video lander where we can drop the video cameras down on a frame and leave it, and then we can get video of the seafloor. We've also used this device, which is a plan view. So it's got a camera that looks down and will take a photo of the seafloor, but then also a sediment profile imaging. So there is basically this part of the device penetrates the seafloor, and there's a piece of glass here and the camera inside. And so you can get a picture of down in the sediment, and you can see things like burrows and where the really oxygenized layer is versus the less oxygenated layer. And then the main thing we do in terms of collections, our box core collections. So this is our box core. We'll grab a bit of seafloor, sieve the sediment out, pick all the organisms off the sieve, and then in the lab, we identify and count the organisms. Oh, there we go. So as I mentioned, BOEM sponsored in 2010 through 2012 surveys all along the coast. We also took data that had been collected by the EPA in 2003 and reanalyzed that. So it was pretty cool because we had these data from 2003 and then almost 10 years later from 2010 to 2012. And then we've also seen, also with our PacWave North sampling, able to characterize some places where we would expect to see transition communities and that they're related to wave energy. So this can help us focus efforts on where we might expect to see changes from the PacWave project. So here in 2013 through 2015, as we were in meetings for our license application, we took a lot of box core samples all off the coast of Newport. And what we found was that within the PacWave site, it's quite similar to areas north and just inshore and south. And so we can feel confident that we can use areas outside the box as reference areas for changes that might be occurring inside the box. As I mentioned, we did some additional opportunistic sampling from 2019 to 2022 to keep the time series going. So in each of these maps, all these little dots are box core samples that we've taken over the years. And then in 2023, because we knew we were laying the cables in 2024, began our official license required sampling. So all along what would be the future cable route and in the site, really just want to fully characterize it. And then in 2024, we went out before the installations and then after the installations. So really focusing on the cable route because that was the impact in 2024. Here's what we found pre-installation. And so the line colors represent different months of sampling. I see my figure legends are really small. But crustaceans, for example, amphipods and shrimp, and bivalves, for example, small clams, they increase in abundance with depth with little variability among seasons. But other species, the response to depth in worms and snails varied across seasons. And so that's why it's super important if we laid the cables in the fall that our post-installation samples that we take in the fall be compared to the fall before and not the spring before, since we see that natural variability among seasons. Echinoderms, generally mostly sand dwellers, generally decrease with depth, except in the fall when their densities are lower overall. And sea anemones decrease with depth, but only in the summer because they're not there in the spring and the fall. So understanding these patterns with depth and season are important before we try to detect effects.
Sarah, just to clarify that one axis is depth, like depth along the cable route as you go down towards the site?
Yes. So
Okay.
not depth in the sediment. Good clarification, Sarah. So
Okay.
yeah, so this end, so small depths like 25 meters is where the cable route starts. And then we're basically going towards the site as we move offshore and get to like 70 meters of water. Good
Okay.
clarification. Thank you. So now I get to share with you pre versus post installation patterns. So this is just a subset of the samples where we sampled basically the same station before and after. And so here again is depth moving from the start of the cables to the end of the cables, and the median grain size. And there's very little pattern with depth and very little difference between the 2023 in 2024. They kind of diverge in the shallower area, but there's so much variability. That's what this shading is that statistically they're not different at all. And then if we look at the organism groups that I shared with you before, statistically, there's no differences in any of the groups. But interestingly, both the bivalves, the small clams, and the snails, there were slightly more in our post-installation sampling. But of course, we would need to compare that to long-term trends to see if this is a trajectory that we've been seeing over the years or specific to these 2 years. So our next step are to identify the samples to the species level. So instead of looking at all the clams together, looking at, say, specific clams. We know from our earlier work that this clam on the left, it doesn't care what the sediment is like, but is only found deeper than the winter storm wave base. So if we were to change the wave conditions, we might expect to see a response. So we wouldn't expect to see a response in that species yet, since all we've done is lay the cable, but would be something to monitor for the future, as opposed to this clam on the right that has really strong sediment preferences. It will not tolerate any silt being in the environment. And so that's something that we could track as a species to say, oh, are we changing the sediment in a way that matters to species? We have now completed the spring 2025 samples, and so we can compare them to the spring 2024. Yeah, I'll note that the cables are not energized because there are no wave energy devices out there. So we're really only looking for the effects of the cable installation, because right now they're just objects under the seafloor. So no wave energy devices at the site yet. Is there a possibility of artificial reefs? Certainly, and that is one of the elements of our monitoring plan that will go into effect when we have wave energy devices and their associated anchor systems put in place. So we've been just doing some video surveys of the open space that's out there right now, but we'll really ramp up those video efforts once there are devices. So next steps for PacWave. There are no devices out there now, but we have launched a call for a commercial manager to help recruit developers to come and test at the device. So if that's the kind of job that you or someone you know might be interested in, that is open now. And we are also seeking a qualified electrical contractor to support operations at the facility once devices are in and they start generating electricity. So important, nothing except cables, basically long extension cords, are at the site right now. We hope someday, so this is a drawing of what we anticipate sometime in the far future, is that each of these blue lines are cables that are coming into the site, and a wave energy developer could deploy as many as 5 devices. But at the moment, we're just hoping maybe soon one device could come to our site and prove our concept and start generating some electricity and give me some artificial structures to monitor for reef effects. So that concludes my portion of the presentation. little bit long, but I think we've still got about half an hour for questions.